So today I'm talking about what we kind of worked on for the last month or so, just wrapping SIRF in PyTorch, but this is purely the Python interface. So it's really an exercise of reading documentation, which is what I'll briefly talk about. So we have the wrapper as well. So if you're curious to have a look online and just see how it's implemented, you can follow this URL. So what is wrapping? So the core idea, like what Chris was saying, is that we have some really interesting operators in SIRF, like particularly for MR and for PET, and you can go from the raw scanner measurements to some image, and that's all done through SIRF, through some very sophisticated, very smart people over a long period of time have been working on this. And the idea here is that we want to use that through PyTorch. So we want to integrate SIRF's forward and backward methods into PyTorch computational graph somehow, so that we can use it for reverse mode autodiff. And this is predominantly done through subclassing one thing in PyTorch, which is called torch autograd.function on the Python side. And this is basically an exercise of reading documentations, making sure that how you call things in SIRF is then translated to how you call things in Python. So well, I'll go through in more detail, but I'll give you an example first of something we would want to do. So an example is we have some neural network, for example, so which we denote as G. So it's got some parameters. So network parameters are theta, and we have some input to the network. So think about like a UNet, for example. So we have an input, which is an image, and we have some parameters, which are theta. And this network outputs an image, which is X. When we have some objective function, for example, comparing some discrepancy term between your actual raw scanner measurements, or perhaps this operator isn't necessarily between an image domain and a measurement domain. Maybe it's some registration operator or something else. It's just some idea that we have some operator and we have some adjoint of it as well. And the objective function in that case is some discrepancy between what you want and what your output of your neural network forward projected gives. So your forward model, for example, in this case, in PET, it would be some sort of weighted line integrals and some other factors which are very specific to PET. For MR, it would be some sort of Fourier transform. And then the forward projected is we take the output of our neural network, so which I denote as X, which is that GZ given theta, and we forward project that to give you Y bar. And then the optimization, this is just an example, but for example, we'd want the output of the neural network when forward projected to align in some distance, some metric to your raw scanner measurements. And you want to update your parameters of your network to create an output, which is then forward projected close to those measurements. And in deep learning, we often use first order optimization techniques, so where we only require the gradient. And very briefly, how the gradient's computed in PyTorch is we use backpropagation, which is a very fancy chain rule with some really nice algorithms in there. But we want some derivative, so that's our objective function. So that thing what measures the discrepancy between your real scanner measurements, for example, and then your forward projected output of your neural network with regards to your parameters. So you want to get that gradient. So first, Y bar, remember, is the output of your neural network. So you take you get some column vector, which is your scalar objective function, and you with regards to your Y bar, that gives you column vector, and then in the backprop, you use the chain rule, then you get your Jacobian of your A, so your derivative of Y bar given X, and take the transpose of that. And then you take that, and then you do the chain rule again to the next step, and then you take your derivative of X with regards to theta now. And the idea here is that we know that PyTorch is very good at handling some idea of your Jacobian in regards to your parameters theta, and then we have SIRF, which is very good, or applies this, which is your Jacobian in regards to A transposed. And in SIRF, we already have access to all these things because we do typically some first order optimization to create our reconstructor image, and we also have access to the Jacobian adjoint, and specifically for linear forward models, So something like a radon transform or Fourier transform, the Jacobian is A, and then the Jacobian adjoint is simply the matrix transpose. So we can wrap those things really easily in PyTorch now. And one thing to note is the Jacobian is never explicitly formed. We always use some implicit method because these Jacobians are humongous. For example, like the number of sinogram bins by the number of voxels in your image, this thing's going to be very, very large. So instead, we use using PyTorch terminology, we use the Jacobian vector product. So we don't never compute anything. We just compute the application of a vector on your Jacobian or your vector on the Jacobian. I said the same thing twice. I mean, I was going to say it the wrong way, the other way around. But and then what's very important to notice also is that in SIRF, we have some data container type, which is not necessarily compatible with that in PyTorch. So we always require copying from the SIRF data format to the PyTorch data format and vice versa within these operations. So that's where the overhead comes in, because we're copying off the GPU out of VRAM into RAM and then back from RAM into VRAM and stuff like that. But then even within SIRF, we have CUDA accelerated projectors, for example. So then we have to do that copying again. So you end up copying 4 or 5 times with four times every single forward pass and every single backward pass. So that's the thing which is really at the crux of what we want to improve on, I guess, or part of it, I should say. So now getting to the actual function. So just going through the documentation. So this torch autograd function. So there's a forward method. So the forward method is when we're essentially applying our linear operator, and the backward method is when we're applying the joint over forward operator. And these are the two main methods we need to define when we're integrating PyTorch, integrating SIRF within PyTorch. And there's a few steps which we need to make sure that we're doing correctly. So instead of self for torch autograd function, we have the context property. So making sure that that's set up properly. So making sure that if we have tensors, we save them to backward in a specific way. This isn't necessarily to do with double backward, actually, but
forward and backward, that simplest thing to do, right?
Yeah. So forward is like when you're applying your operation. So yeah, it's like direct, and then backward is when you're applying a joint, for example. Yeah. So it's just, and within those methods, for example, in PyTorch, you'd have a PyTorch tensor. You take that PyTorch tensor off your GPU, then you convert it to a SIRF data container. Then you take that SIRF data container, pass it through SIRF, and then do the forward projection. Then you take it off out of the data container and pass it back into PyTorch again. So it's these swaps which it'd be interesting to try get rid of because it's very costly. But I'm curious at how costly they are compared to the full projection operators as well. Like relatively, they might be relatively small. And then for the CTX, so the context variable in your torch autograd function, you have to be very careful about how you're using things so you don't break the gradients effectively. And instead of going through each one of these, maybe if you have questions, you can ask me or refer to the documentation as well. And then you can also say whether it's once differentiable or something like that. And then it's always very important to double check your gradients are computed properly. So grad checks the best way of doing this. So it computes your Jacobian numerically, which can be very costly when you have very large images and a lot of data, but it's the best way to check things, and then compare against your vector Jacobian product. And this is all in the documentation. So something I thought I would just add in because it's kind of interesting is how PyTorch tensors work a tiny bit on a very, very brief, very, very high level overview. But you have your tensor operation somewhere. So for example, this is a case of torch matrix multiplication, which happens so much in neural networks, but you have to dispatch this dynamically in some sense. So you can use it on the CPU and the CUDA and all the different kernels, which are very optimized specifically for these applications and the different data types as well. And how this looks in PyTorch is there's part of PyTorch which is called A10, which is shortening of a tensor library, and it has all the C++ and all the rest for example, for add-out, you have CUDA support and you have CPU support. So they've already implemented lots of kernels to do things very effectively. So to do things very fast, for example, on a GPU and a CPU, and perhaps other hardware as well. And then I was sort of debating whether to have this last slide in, but I don't know how much time do I have? Yeah.
Oh. Okay.
Okay, yeah, but like the last thing, which I think is a big thing in deep learning at the moment, is that there's lots of very, very smart compilers coming out at the moment, which I don't know we aren't really, I haven't seen very much adoption of using these for medical image reconstruction or something like that. But the idea that we can write metacode in some sense and then pass it all to some JIT compilation, which will hopefully put on your TPU or your other GPU or AMD or something like that, because there's so many different types of ways of accelerating things nowadays. Maybe writing CUDA kernels, although it's so like efficient and it's a very difficult thing to do, to get things so they work across many different devices is an interesting prospect for the future. Yeah, but that's all these things like Triton is I don't have to pronounce it, but like that's like from OpenAI, so they own the roadmap in a sense, although it's open source, and all these other things, they own the roadmap. So necessarily the right things that get into the code might not be what we want to use, and maybe that's not a good framework to use. But it's just interesting that all these things exist, and how can we take better advantage of all the software which is out there as well. But that's where I'll end it, I guess.